As an example of an incremental approach to algorithm design, let's look at the insertion sort algorithm. So you already saw how insertion sort algorithm works. So basically, here's the pseudocode or the code for how the insertion sort works. The idea is to pick a key from the unsorted part of the array, right? Unsorted part of the array and place it into the sorted part of the array. And we pick a key, the key that we pick out from the unsorted part, say for example, here is 3. And then after that, we sort of scan back the sorted array to find a place to keep the key. And this part is done by the second while loop, which is inside the for loop. So this is basically how insertion sort works. And the outer for loop goes from the second item all the way to the end of the list, from 2 all the way to the end of the list. And this while loop executes until it finds a match to place this key. If it's already sorted, it might find it ahead of time. If not, it might go all the way to the beginning of the list. Now let's see let's look at the running time of the insertion sort algorithm. So here's the algorithm on the right hand side. Now the total execution time of this algorithm is determined by how many times the outer for loop runs times how many times the inner while loop runs. So it's the number of times the for loop runs is executed times the number of times the while loop that's inside is executed. Now, we know that at the beginning, when we have this entire list, only the first item is assumed to be sorted. Then we pick the second item, put it in the list. Then the first 2 items become sorted. And that's how the sorted part keeps growing, right? So the number of times the while loop is executed is at the beginning, the while loop is executed only once. In the second time, it's executed twice, thrice, and so on. So the number of times while loop is executed is the total number of times the while loop is executed is 1 plus 2 plus 3 plus da 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 up to n minus 1. So clearly, this is sum of natural numbers, sum of natural numbers, which approximately is equal to n times n minus 1 divided by 2. This is approximately the sum of this. So this is how much time it takes to execute the while loops, right? Clearly, there's any square term here, right? So now what we have is, if we look at the running time of the entire insertion sort algorithm, where your dot length or n is the number of items we have in the list, then this thing, let's say, for example, this part takes X time, then since we do this for each item, almost approximately each item, the time taken by this part will be X times N. We know that this part takes some constant, so this part takes N times approximately N minus 1 by 2 time, which we could say is approximately, say, A times any square time plus B times N time, right? And then we also have something here, which is also run for each item. So this may be something like Y times N. So essentially what we have is a square term with some constant, a linear term with some constants, which can be all summed up. And then the whole algorithm may need some time to load, right? There may be other parameters that are constant for the entire algorithm. So we can say that the total time taken by this algorithm for n items will be a constant times n squared plus a constant times n plus c. So this is the running time of our insertion sort algorithm. Now there are best case and worst case scenarios. If the list is already sorted, let's say 1, 2, 3, 4, 5, 6, da da da, then what happens is, as we pick the key from our list randomly, we only need to go one step back to place it in the right place. We don't need to go all the way down. In other words, this while loop does not need to be executed more than once, right? So if the list is already sorted, then the running time becomes better. It runs faster because it's already sorted. Now, the worst case scenario is when the list is already reverse sorted. So if we have the largest item here, 10, 9, 8, 7, 6, and so on, then each time the inner while loop has to go all the way from the beginning where it picked the key to all the way to the beginning of the list, right? So insertion sort does have some worst case scenarios where the algorithm might shine, so sorry, the worst case scenarios where the algorithm might do very, very terribly in terms of the speed, and best case scenarios where the algorithm might shine. So what we just saw was the insertion sort algorithm, an example of an incremental design of algorithms. Now, next, what we're going to see is an example of a divide and conquer approach to algorithm design, and we'll use merge sort as an example. This is because many algorithms which are useful turn out to work well when they are designed in a recursive way. And what we will see now is a recursive structure in algorithms. So the divide and conquer approach to algorithm design involves 3 steps. The first step is to divide the problem into a number of subproblems. There are smaller instances of the same problem. So say I have a problem to sort, let's say, n elements, right? N elements. Then the first step of dividing is to break the problem down into either 2 pieces or maybe 3 pieces, right? But basically, the task here is to divide the problem into subproblems. But the subproblems still are the same nature. That is, if we divide this into 3 pieces, then and if we are left with n by 3 items each, then the task now becomes sorting these n by 3 elements. The next step is to conquer the subproblem. That is, what we want to do is, given this n by 3, if the task is to sort, then we want to get this sorted. And the last step is to combine the solutions. That is, assuming that we had n items, and we divided the n items into n by 3, n by 3, and n by 3 pieces. Then the last step is, assuming this is sorted, also sorted, and this is also sorted, is to combine all 3 and get the solution for the entire n. Now let's look at the merge sort algorithm and see how this design of a divide and conquer approach applies to the merge sort algorithm. So basically the operation in merge sort is exactly the same. We first divide, that is, given an array of elements like these, we divide the element into 2 subsequences of each n by 2 elements. So we break it in the middle, and then we've divided it, right? We divide it and we break it into 2 lists that need to be sorted. The next step is to sort the 2 subsequences using the merge sort algorithm. So if we look at the algorithm, given an array A with starting index P and the ending index R, what we do is we check if we have at least one item by checking is P less than or less than R. And then we break the array into 2 pieces, right? But to take the middle element index, Q, which will go in the middle. And then we merge sort the first piece from P to Q. And then we merge sort the second piece, Q to R. And then once we have sorted the first piece, the first part and the second part, and then we call the merge algorithm to actually merge 2 sorted pieces. And that's the combined part. So this is how the merge sort algorithm works, and it follows the divide and conquer approach. What we are interested in is to understand or to investigate the running time of the merge sort algorithm. Now, it turns out that because of the complex nature of the merge sort algorithm, as you can see, it's recursive in nature, right? So merge sort calling merge sort itself, right? So because of the recursive nature, it's very difficult for us to determine the running time of this algorithm. So to calculate running time, what we need is for algorithms like these, which follow the divide and conquer approach, we need to develop or understand the recurrence equation involved, and then also build something known as a recursion tree, which we will get to. But once we have a recursion equation and a recurrence tree, then we can use those information to calculate our runtime. So say we have a list like this, right, which 5247136, and what we would like to do is run the merge sort algorithm on this list. So obviously the first thing we will do is divide the list into two, right? The first list and the second list, first half and second half. Once again, the algorithm says we divide, right? And then divide again. So this is the first single element list that is supposedly already sorted. So then as the algorithm winds up of recursion, right, 5 and 2 need to be merged because 5 is already sorted, it's the only item. 2 is also already sorted, it's the only item. So then we call the merge algorithm to merge them. So 2 and 5 are sorted. Similarly, the next sub list has 4 and 7, that's sorted. Those two are merged, so this becomes a sorted sub list and so on. Now, after these two are sorted and these two are sorted, we have two sorted sublists. Once again, we merge them. We merge the second sublist as well. And finally, we have two lists that are sorted, right? And we simply need to merge them. So this is also sorted. This is also sorted, and we just need to merge them. So now if we wanted to look at the running time of this algorithm in terms of the number of inputs n, that is the size of this input array, then we can actually express the running time using this recurrence equation. At the end, when we have only one item or a fixed number of items that can be solved at once, we say that the running time is some constant. We will get to this theta later, but we can assume that this is some constant running time because we can always solve those many number of items when we get to the bottom of the recursion, right? Otherwise, the running time of the algorithm with n inputs is equal to whatever number of pieces we broke the problem into. In this case, since we broke the problem into two pieces, it'll be every time we break the list into two pieces, it'll be 2 times the time taken to sort one sub piece. So in this case, time taken to sort this piece times 2, because we have two such pieces. Excuse me. So basically what we have is time taken by the entire algorithm for n items is equal to the number of pieces times time taken by each sub piece, right? So each sub array. Now, every time we break the list into sublist, what we are doing is we are also taking time to divide the problem into sub problems, right? So this is the time dn that we calculate. Usually this is a linear time, but this is the next time that we need, that is total time that should be added. Also, when we are first splitting the list, this is dn is the time needed to divide the problem. And then once this is solved, assuming that we have the solution for the subarrays, we need some time to combine the solutions. That is, for example, the merge algorithm that's needed. That's Cn, right? So essentially what we have done is, for an algorithm that has this divide and conquer approach that usually follows a recursive approach of solving the problem, we have expressed the running time of this algorithm in the form of a recurrence equation where the running time is itself like a recursive running time. So this is a general form for all divide and conquer approach or all recursive type algorithms. But then for the specific case of merge sort, we know that every time we break the problem into only two pieces, right? And every time we get a new list that is equal to n by 2, that is half of the original list. So the running time of with n inputs is equal to a constant when n equals to 1. That is, we don't need to sort when n equals to 1, so some constant running time, right? or when n is more than 1, 2 times the running time for half the list. So if the running time for the original list was 10 seconds, then this would be 5 seconds and so on. Also, in the merge sort, we don't need much time to divide the problem because we don't need to copy the entire array or do anything specific. What we do need time is to combine the solutions. And this we know that the merge method takes approximately Cn time, linear time. So this is the recurrence equation for the merge sort algorithm. So with the help of this recurrence equation, what we can do is build a recursion tree. So what we know is that the total running time for the algorithm is Tn, which we know is expressed in terms of 2 times Tn by 2, running time of n by 2 size array plus Cn. So this is Cn. So the total running time is Cn plus running time for half of the array and running time for the remaining half of the array. So if we sum it all up, that gives us the total running time of the algorithm. We can further go down deeper into the recursion tree and express that the total running time is Cn plus the time to combine the solutions for n by 2 items, again n by 2 items, and then the running time for n by 4 items times 4, right? So if we expand this recursion tree, what we can do is actually analyze the recursion tree to come up with the entire, to calculate the entire running time. So here's a full-blown recursion tree. So the running time becomes Cn plus Cn by 2 plus Cn by 2. This is simply the time to combine or merge solutions when the entire list is n by 2, right? And so on all the way to the end, right? Where the running time for each item because of the constant C is only C. So you can see that in this recursion tree, at every level, the total execution time is Cn. This also sums to Cn. This also sums to Cn. And at the end or the leaf nodes of the recursion tree is also Cn, right? So at every level of the recursion, every depth of the recursion, the running time is Cn. So we see that the running time at each level of the recursion tree is Cn, right? Now the next question is, so how deep is this tree, or how big is this tree, or how deep is this tree? Now, we know that at every level of the tree, we take n items and break the items into 2 each time, right? So basically, if we had 8 items, we would break this into 4, 4, and then 4 would be broken into 2, 2, 2, 2, and then 2 would be broken into 1, 1, 1, 1, 1, 1, and so on. So what we essentially have is actually the depth of the tree. We can easily see the pattern here is actually log n. This is basically log 2n, right? So log 2 is also written as simply lg. Um, and the height of the tree is simply log 2n plus 1. So this clearly gives us, we see a pattern here and we can calculate the height as this way. So then the total running time is Cn times log 2n, right? Log 2n plus 1. So this would be total cost equals Cn times log n plus 1. So from this, what we will get is if we multiply these constants, then you will see that the Cn or constant times n log n plus a constant times n. This is also to compensate for the fact that there may be some time needed to do the splitting that we didn't earlier calculate, right? So the running time for the merge sort algorithm for n items can be expressed using this equation now. We took the help of a recursion tree and a recursion equation to come up with this running time. Now, are there best case and worst case running times? The answer is a no. That's because regardless of whether the list is sorted or not, we always execute the entire recursion tree and we go all the way to the bottom. So merge sort does not have best case or worst case running time. No matter whether the input is sorted, already sorted, or reverse sorted, or it is completely random. It always takes almost the constant time, the same constant time, regardless of whether the input is sorted or not.